Bismillahirrahmanirrahim. In our previous session, we discussed the concept of push out. Today, we are going to discuss pullbacks. The concept of pullback is dual to the concept of push out. So, in order to understand what pullback is, let us recall the definition of push out. So, let us recall the definition of push out. In a category C, in fact. And we know that the diagram this particular diagram A, B, C, D, these are the objects, and F is a map from A to B, G is a map from A to C, and we have maps from C to D beta and B to D alpha. So this diagram is called push out of F and G. In fact, we mostly say in this way. So this diagram is called push out diagram if we have two conditions. First of all, you know that this diagram has to commute, which means that alpha composed with F is equal to beta composed with G. And the second condition is for any maps from B to X, let's call this map alpha dash, and from C to X, let's call this map as beta dash. X is an object of the category C. So for any maps alpha dash and beta dash such that alpha dash composed with F is equal to beta dash composed with G. To understand what does this mean, is better if we draw the diagram. So this is the diagram we already have. So this is the diagram from A to B. We have map F. From A to C we have map G, and then from B to D we have map alpha, and then C to D we have map beta. So the condition says that if there is an object X and maps from B to X and C to X, these are alpha dash and beta dash, such that alpha dash composed with F is equal to beta dash composed with G. So if for some object X there are maps alpha dash and beta dash such that this condition is satisfied, then there exists a unique map from D to X. We denote it by theta, such that you know that theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. This map has to be unique. Then there exists a unique map unique map from D to X. We have denoted this map by theta. Then there is this a unique map from D to X such that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. So if these conditions are satisfied, then this particular diagram is called push out diagram. As we have already discussed, that the concept we are going to discuss now is that of pullback, and this concept is dual to the concept of push out. So we have already noted that in this session we are going to discuss the concept of pullback, and pullback is dual to push out. And you understand what duality is. Since pullback is dual to push out, so in order to define what pullback is, all we have to do is that we will reverse the arrows in the definition of push out. So in order to see what pullback is, let us reverse the arrows. Arrows of diagrams in the definition of push out. So the diagram in a category C will be pullback. The diagram let me show you the diagram which we used for push out. Arrows from A to B and A to C. Now we will draw a diagram with arrows from B to A and C to A, and then from D to C and D to B. So the diagram in a category C let's draw the diagram. We have objects A and B and arrow from B to A, F. It does not make difference if we retain same names as we use for push out, because this is a new definition, so F will have its own meaning here. So arrow from, important thing is that we are going to take arrow from B to A. So, and arrow from C to A, which is G, and then we have object D and arrows from D to B and D to C. Let's name these arrows again alpha beta. It will not make any difference, but important thing to note is that in case of push out, this is the way we had arrows from A to B and A to C. Now we have arrows from B to A and C to A. In case of push out, we had arrows from C to D and B to D. Now we have arrows from B to D to B and D to C. So just note the reversal of the direction of arrows. So then this particular diagram is called pullback. Pullback of F and G. So pullback diagram. If we have similar two conditions as we had in case of push out. So first condition is the same condition, that this diagram has to commute, and that means that alpha composed with F composed with alpha. We will have to go in this direction. F composed with alpha is equal to G composed with beta. G composed with beta. And then second condition is for any maps from an object X to B, let's call it alpha dash, and from object X to C, let's call it beta dash, such that F composed with alpha dash is equal to G composed with beta dash. You will be understand it in better way if we draw the diagram. So let's do that. So in order to understand that, let's draw the diagram. We already had this part of the diagram, that is arrow from B to A, then arrow from C to A, then we had an object D and arrow from D to B, and arrow from D to C. These arrows are F and G, and these arrows are alpha and beta. So what we are saying now is that if there is an object X and arrows from X to B and X to C, so just note that if there is an object X and arrows from X to B, from X to B and from X to C, and from X to this arrow from X to C. Let's call these arrows alpha dash and beta dash, such that we have written that such that alpha F composed with alpha dash is equal to G composed with beta dash. F composed with alpha dash is equal to G composed with beta dash. We have already written that. And then there exists a unique map from X to D. Let's call this map again theta. Then there exists a unique map from X to D theta such that now theta must satisfy these two conditions, that alpha composed with theta should be equal to alpha dash, and beta composed with theta must be equal to beta dash. So this is the definition of pullback, which is dual to the definition of push out. Having defined what a pullback is, just note that we may also say that in a category C, the following diagram which I am going to draw now, so we may also say that in a category C, the diagram or the following diagram so let me show you the diagram of pullback we have discussed. This is the diagram of pullback we started with. I'm going to draw the same diagram, and the difference I will tell it, there won't be any difference except certain position of the objects. So what I'm going to do is that I'm going to draw this diagram. We have object D and object B, and arrow from D to B. Then we have object C and arrow from D to C. These arrows are alpha and beta. Then we have arrows from B to A. This is arrow F. And we have arrow from C to A, and this is arrow G. Just note that we have drawn the same diagram as we have already done. There is arrow F from B to A. There is arrow F from B to A. There is arrow G from C to A. There is arrow G from C to A. Alpha is an arrow from D to B. Alpha is an arrow from D to B. And then beta is an arrow from D to C. Beta is an arrow from D to C. So this is the same diagram. So the following diagram is called pullback of F and G diagram if same two conditions. First of all, the diagram has to commute, and that means that F composed with alpha is equal to G composed with beta. In fact, writing diagram in this way will make slightly things simpler, because these are the way we are mostly habitual of seeing the diagrams. So this is the first condition, and the second condition which we have already seen. In second condition, for any maps from an object x to b, we call this alpha dash, and from the same object x to c, we call it beta dash, such that f composed with alpha dash is equal to g composed with beta dash. To see this, it is advisable to draw the diagram first. So I will reproduce the same diagram which we have already discussed, this one diagram. So we have object D, and we have object B. We have arrow from D to B, which is alpha. We have arrow from D to C, which is beta. Then we have arrow from B to A, which is F. We have already denoted it by H, and arrow from C to A, which we denoted by G. Now if there is an object X and arrows from X to B, arrows from X to B, this arrow is alpha dash, and arrow from X to C, this arrow is beta dash, such that f composed with alpha dash is equal to g composed with beta dash, this condition. Then there exists unique map from D to X, is very important. This is called universal arrow. So then there exists unique map from X to D. Then there exists unique map from X to D. Unique map from X to D. So then there exists unique map from X to D. We called this as theta. Such that alpha composed with theta is equal to alpha dash, and beta composed with theta is equal to beta dash. So we have written the same definition of pullback which we have already discussed. We have simply changed the locations of objects A, B, C, and D, and what is important, that is this universal arrow theta. Note that when we used this diagram, and this we defined it as pullback of F and G, then arrow was from X to D, because D was at this end, and the diagram is pullback of F and G, so arrow was from X to D. We have same thing again. This is pullback of F and G, and D is at this end, so universal arrow has to be defined from X to D, and this is unique arrow. So I have tried to write two possible ways, not in fact the same way of writing the definition of pullback. I simply want to convince you that the important thing is this universal arrow, and this universal arrow has same position as it is in our previous attempt of defining pullback. So this is the important thing. The universal arrow is the important thing. So just note this universal arrow. So this was definition of pullback. So let me compare these two diagrams. In fact, these are the same diagrams. I simply want to emphasize the way they look. So I will need more space, so we go to next page. Anyway, we noted that the diagram we are going to draw, note that the diagrams we are going to draw on the next page. Convey the same concept, that is pullback. Convey the same concept, that is pullback. And though the diagrams look different, but effectively they are the same diagrams. And effectively these are the same diagrams. Both diagrams are same. I am just going to repeat the diagrams we have already discussed. So let me divide this page in two parts so that diagram look opposite to each other, so it will be easy to compare and to see that these are the same diagrams. So recall that first of all what we did is that we started from this diagram. We had arrow from B to A. This arrow was F. Then we had arrow from C to A. This arrow we denoted it by G. Then we had an object D, an arrow from D to B. We called it alpha, and arrow from D to C, we called it beta. So in a category C, the above, this particular diagram has to satisfy two conditions in order to be a pullback diagram. So is pullback, this diagram is pullback of F and G diagram if there are two conditions. First of all, F composed with alpha is equal to G composed with beta. G composed with beta, that this diagram has to commute. And secondly, for any maps from an object X to B, this is alpha dash, and from the same object X to C, and we denoted it by beta dash. such that f composed with alpha dash is equal to g composed with beta dash. Let me draw the diagram first. So this is the commutative scale we have already discussed. So map from A to B, this is F, then map from A to C, and this is G, then map from B to D, and this map is alpha, then map from this map from D to B, sorry, map from D to B, so just forget about this one. So map from D to B, this is alpha, and then map from D to C, and this is beta. And for any maps from X to B and X to C, so if there is an object X, and there are maps from X to B, this map is alpha dash, and there is map from X to C, this map is beta dash, such that this condition is satisfied, that is f composed with alpha dash, this composition is equal to g composed with beta dash, this composition. So this composition is same as this composition, these are equal. Then there exists unique map from X to D, unique map from X to D, this is theta, from X to D, which is theta, such that alpha composed with theta is equal to alpha composed with theta is equal to alpha dash, and beta composed with theta is equal to beta composed with theta is equal to beta dash, and beta composed with theta is equal to beta dash. So this is the concept of pullback which we discussed first of all, and I slightly relocated the objects, and the diagram we obtained is we have D and then B, then arrow from D to B, which is alpha, then arrow from D to C, which is beta, then we have arrow from B to A, which is F, then we have arrow from C to A, which is G. So this diagram is pullback of F and G. So this is pullback diagram. If conditions are same, the diagram has to commute, and that is F composed with alpha is equal to G composed with beta. And secondly, for any maps from an object X to B we name it as alpha dash, and from the same object x to c we name it as beta dash. Let's draw the diagram. So this is the diagram we have already drawn. Let's take this diagram at this place because our universal arrow is going to be from x into d, so we need space above. So this is d, and then we have map from d to b, which is alpha. Then we have c, and map from d to c, which is beta, and then we have map from b to a, which is f, map from c to a, which is g. These are the important maps. In fact, this is pullback diagram of f and g. These maps are the important maps. So you will see these things when we will discuss examples. You will be able to understand and the importance of these maps. So for any maps from x to b and x to c such that f composed with alpha dash is equal to g composed with beta dash. So let's complete the diagram. So we are talking about an object x. So this is the object x, and then we have map from x to b. So this is map from x to b. This is alpha dash. Then we have map from x to c. So this is map from x to c, which is beta dash. And these maps have to be such that f composed with alpha dash is equal to g composed with beta dash. Then there exists unique map from x to d, such that, so especially note this particular map which is from x to d. This is the map from x to d. This map, this is called universal arrow. So there has to be a unique map from x to d theta such that alpha composed with theta is equal to alpha dash and beta composed with theta is equal to beta dash. So if you see these two diagrams opposite to each other, you can see that these diagrams convey the same concept, and that is concept of pullback of arrows f and g. Pullback of arrows f and g. That is going to be this object d, and then these arrows and these things. Pullback of f and g is going to be this object d with these arrow, this particular universal arrow. So so having discussed the definition of pullback, let's see a few examples. And example 1. We take this example from the category of groups and group homomorphisms. So consider the category. We denoted this category by G or P. So consider this category, which is category of groups and group homomorphisms. And we know that category of groups has zero object. Zero object is an object which is initial as well as terminal object. And zero object in the category of groups is the trivial group. You can denote it by with two brackets and inside E, or you can denote it by 0. 0 is the most common notation for zero object. So consider this category which has zero object, and we denote this object by 0, capital O, call it capital O. Also note that in the category group, pullbacks exist. Further note that pullbacks exist in this particular category of groups and group homomorphism. Then in the following diagram, in fact I'm trying to retain the same diagram and then replacing objects according to our purpose or according to our category. So then in the diagram we are using in order to understand what pullback is, and you know that diagram is this one: object D, object B, and we have morphism alpha. Then we have morphisms from D to C, which is beta, and then we have object A and morphism from B to A, which is F, and then morphism from C to A, which is G. So this is the diagram we have defined as pullback diagram, provided that universal arrow condition is satisfied. So in this diagram we are going to take B as B as zero object. So then now you have to revisit your previous notes, or you have to revisit the books you have with you, that if B is zero object, then these two maps alpha and beta are just obvious maps. You know that what zero object means, and then you can see what these two maps are going to be. Then alpha and these two maps, alpha and F. Alpha is map going from D into the zero object, and F is the map going from zero object to the object A, and these are very familiar unique maps. Then alpha and F are obvious maps. Just go to your books and see what zero object is and what these maps are going to be. So take B is equal to zero object, and then take D, this particular object, as kernel of this map G. Kernel of. So take D is equal to K, where K is kernel of this group homomorphism G. Then the following diagram in the category of groups is pullback diagram. Then the following diagram in the category of groups is pullback diagram. So instead of D, we are going to take K, which is kernel of this map group homomorphism G. Instead of B, we are going to take the zero object, and then we have C and A, and we know what this map F is going to be, and we know that this map, what this map alpha is going to be, and this is the group homomorphism G, and this is kernel of G. So this map is just going to be inclusion map. When we represent inclusion map, we simply put a slight curve here. So this is inclusion map. You know that kernel is subgroup of domain. So kernel is subgroup of C. So this is inclusion map. We denoted it by beta. So let's keep the name beta, but beta is inclusion. I note it here where beta is inclusion map. So in order to see what universal arrow is going to be, I will simply draw the diagram and leave the rest for you to understand what all these things mean. So for universal arrow, consider. So you know what the diagram is going to be. We have the same diagram from K to the zero object, then from zero object to A, which is obvious map, and this is obvious map as well. This is group homomorphism G, and this is kernel of G, and this is going to be subgroup of C. So this is inclusion map beta. And if there is an other group X and maps from X to zero object, and you know that what this map is going to be, and the map from X to C, I will have to simply give a little curve here, and map from X to C, which is beta dash, such that alpha dash F composed with alpha dash is equal to G composed with beta dash. Then there exists unique map from X to K. Unique map from X to K, we denoted by theta. From X to K, we denoted by theta, and such that alpha composed with theta is equal to alpha dash, and beta composed with theta is equal to beta dash. So what this theta is going to be, I simply write here hint for you. Theta, effect of theta on any element of capital X is going to be 0, and other details you must work out on your own. Please work out all the details. Prove that f composed with alpha dash, prove that uh, alpha composed with theta is equal to alpha dash, and beta composed with theta is equal to beta dash, and also prove that theta is such unique map. So this is up to you to work out these details and convince yourself that this is a pullback diagram. So we come to another example. Example 2. We take this example again from the category of groups. Again, in the category of groups and group homomorphisms, we have following in the following diagram. So this is the pullback diagram. We have pullback of F and G, and this is the diagram. We have D and B, and then map alpha, then C and A and maps beta, F and G. So in this diagram we are going to take see what this object D we are going to take. So we take D is equal to, take Cartesian product of B and C. So Cartesian product of B and C, and take those order pairs from B and C for which effect of F on B, this B is element of capital B, therefore F is going to act on B. Then C is element of capital C, so G is going to act on C. So we are going to take those order pairs from B cross C for which FB and GC are equal. Note that FB and GC both are elements of A. So we are going to take those order pairs BC for which FB and FC are equal. And you can see that this is subset of B cross C. So we are going to take this D, this particular D as B cross C. B cross C. And alpha and beta are just routine projections, and alpha and beta are projections. Then The above diagram is pullback diagram. So for you, in fact, you have to work out the details. So first of all, what you must do is that replace D by this particular object, just keep it as D, but keep in mind that this D is this particular object, and if you like, you can prove that this is subgroup of this D is subgroup of B cross C. You can prove that. So first of all, I think it is advisable prove that D as defined above is subgroup of B cross C. So this is one of the things you must do. Secondly, show that F composed with alpha is equal to G composed with beta. And thirdly, if X is group with maps from X to B, call this map alpha dash, and from X to C, call this map as beta dash, such that F composed with alpha dash is equal to G composed with beta dash, then this is what you have to do. Then prove that there exists unique map from X to D, let's call it theta, such that alpha composed with theta is equal to alpha dash, and beta composed with theta is equal to beta dash. So this is for you to establish. So this was example 2. Now we come to another example. Example 3. Most of these examples are for you to work out. In fact, in order to understand what category theory is, you have to work out these things on your own. And so far the examples we have discussed, I think you understand each and everything about the concepts in the background, because this is simple group theory. So let's take another example. This again from group theory. So another example, from the category of groups and group homomorphisms. So consider symmetric groups Sn and Sm. We take two symmetric groups Sm and Sn, and you understand what I mean. And let Am and An be the corresponding alternating groups. Be the corresponding alternating groups. In fact, these are subgroups. Am is subgroup of Sm and An is subgroup of Sn, and you know that alternating groups consist of even permutations. You know these things very well. Now consider the group homomorphism. Let's call it psi. So what you have to do is factor Sm with Am, corresponding alternating group, and then factor Sn with An, and take this particular group homomorphism psi, and this homomorphism is isomorphism, which is isomorphism. Now this is your test of group theory. This is your test of knowledge of group theory. To see that why psi is isomorphism. Number one, and then what psi is, you can very easily see it. So this is up to you to determine that. Anyway, so they take this particular group homomorphism, which is in fact isomorphism, from this quotient group to this quotient group. Now in the particular diagram, now in the pullback diagram, and you know what their diagram is. This is D, and then we have B, and then C and A. We have map alpha from D to B. We have map beta from D to C, and map F from B to A, and map G from C to A. So these are the maps we have. In fact, these are the notation we have used for these particular maps. So now in the pullback diagram, take, so this is what I am proposing to take D is equal to sigma delta belonging to Sm cross Sn. This is just Cartesian product of Sm and Sn, and this is also direct product in the category of groups. So we are going to take those order pairs, or those order pairs of permutations which have same signature. You must be knowing this thing, such that Sgn of alpha is equal to Sgn of delta. Just recall that Sgn signum, which assigns, in fact, this signum determines whether the permutation is even or the permutation is odd. So go back and see the definition of signum. So we are going to take those order pairs of permutations for which signatures are same, or value of signum function are same. So take D is equal to the set of these order pairs. Then the following diagram is pullback diagram. And the diagram is, so let me draw the diagram on next page. So at D, you are going to take that particular object I have defined above, that is set of order pairs of those permutations which have same value of signum, for mean signum of alpha is equal to signum of delta. So this is D. Then at place of B, we are going to put Sm. At C, we are going to put Sn, and I will tell you what we are going to put at A. So from D to Sm, this is alpha, this is just projection, and from D to Sn beta, this is again just projection, and then we are going to have these maps F and G. Note that Sm factored by Am is isomorphic with Sn factored by An. So you can consider only one of these two at this place because they are isomorphic. So you can take any one of these. Whatever you take, you can go to other by using the isomorphism. So this diagram where alpha and beta, I have already told you, where alpha and beta are projections, and F and G are canonical maps. This map from Sm to the quotient group, again from Sm to the quotient group, are canonical maps. So exercise for you, prove that the above information